In this video, we're going to talk about electromagnetic force. Our learning target for this lesson is I can describe the relationship between electricity and magnetism. Our essential questions are, how are electric charges and magnetic fields related? What is the right-hand rule? And what happens to an electric charge moving in a magnetic field? So to begin with, we're going to talk about Oersted's demo. If you were in class earlier, we did this demo, and you remember that we had a loop of wire connected to a battery. And when we connected all of that together and turned the switch on, the compass that we had reacted to the wire. We can see how this works here in this diagram. We have this circuit hooked up with an open switch, and the compass is pointing towards natural north. Once we connect the battery in the loop, the compass will then change the direction it is pointing. So this shows us that the wire and the electricity in the wire is causing an effect on the compass. If we reverse the terminals of the battery in the circuit, the compass will point in the opposite direction. We did not necessarily do this. What we did was place the compass above and below the wire and saw that the compass needle changed directions. But this also happens if you change how you run the demo. So if you weren't here for this, hopefully this helps you remember, or this explains it, but hopefully this will jog your memory if you were here for the demo. So let's talk about electromagnetic force. Moving electric charges create a magnetic field. We know that this is true. We know this from when we were talking about magnetic domains because electrons act as tiny magnets. We also know this from doing Oersted's demo. Both of these things have shown that moving electric charges create a magnetic field. So here's our definition for electromagnetic force. Electricity and magnetisms are different aspects of the same force. Electric force results from charged particles, and the magnetic force results from the movement of electrons in an atom. So we're just rehashing what we've talked about when we talked about Oersted's demo and electrons being magnetic. So let's talk about magnetic fields and moving charges. So anytime you have a moving charge, it creates a magnetic field. Now, the magnetic field lines form circles around a straight wire carrying the current. That's what we're seeing in this right here. I'm going to grab the pointer here. We see that the current is moving in this direction, okay? It moves along the wire here. Because it moves along the wire there, we then have these circles form around the wire. These circles, or B, are the magnetic field, all right? So this is why when we place the compass above the wire, it pointed in one direction, and below the wire, it pointed in a different direction. Because this circle, so up here, the arrows are pointing from right to left. Down here, the arrows would be pointing from left to right. So this leads us to something called the right-hand rule. If you point your right thumb in the direction of the current, so in this case right here, the current is moving up the wire, your fingers curve in the direction of the magnetic field. So you see right here, this person's fingers curve this way. So that means that the magnetic field goes in this direction. If you were looking down, this would be counterclockwise on this wire. So we see that how the magnetic field and the current relates. You have to use your right hand in order for this rule to work. So right hand rule. So let's do some examples of this. Take a moment here and draw this in your notebook. This is a wire carrying a current. The current is moving from left to right. And I want you to go ahead, take a moment, draw this, and then draw the direction of the magnetic field. Pause the video and do so. So what you should get is something that looks like this. If we point our thumb in this direction of the current with our right hand, you will see that our fingers curve going in this direction around the wire. And so this is how we would draw the magnetic field around the wire. Okay, let's look now at what it would look like the other way. So take a moment, draw this into your notebook. And then I want you to go ahead and draw the direction of the current. Pause the video now. You should be drawing it pointing down, because if you point your fingers to curve in this direction, your thumb has to point down. If your thumb is pointing up, your fingers are curved in the opposite direction of these arrows. So you have to point your thumb down, and that tells you that the magnetic or the current is moving down the wire. All right, let's talk about forces acting on moving charges. Electric charges are deflected by magnetic fields. The deflection is at a right angle to the direction of the magnetic field and the direction the charge is moving. So we see this charge enters the field and it moves at a right angle. The same thing for this charge as well. And that right angle, because we're in 3 dimensions, is based both on the direction of the charge and the direction the magnetic field is pointing. Positive and negative charges are deflected in opposite directions. We see that in this little image right here. If the charge is traveling parallel to a magnetic field, it will not be deflected. So we're going to watch a quick video that I think does a very good job explaining this to wrap up this lecture.
This experiment shows the magnetic force on a moving charged particle. So here's the experiment. We have a vacuum tube, an electron gun, and a phosphor screen. The electron gun emits a beam of electrons which travel down the tube and strike the phosphor screen, which gives out light. So the blue dot on the screen shows you where the electrons are. We accelerate the electrons through a voltage difference of 1,000 volts, and they strike the screen with a velocity of 20,000 kilometers a second. That's the distance from Christchurch to London in 1 second. Here's the magnetic field. It's just a simple lab bar magnet with an arrow drawn to indicate the direction of the North Pole. So I have field lines coming out of the North Pole, looping round and coming back into the South Pole. Now watch what happens when I bring the magnetic field close to the beam of electrons. You can see that there's a force on the electron beam downwards, and the force is at right angles both to the magnetic field and to the direction of the electrons. And if I bring the magnetic field down from the top, the electron beam is deflected to the side. And it doesn't matter what angle I bring the field, the electron beam is always deflected at right angles. So it's really important that the magnetic field is at right angles to the direction that the electrons are traveling. If I bring the field along the same direction that the electrons are traveling, you can see that there is no deflection. You only have deflection if you have magnetic field at right angles to the way the electrons are moving.